Hi everyone. This is the second lecture on the step response of inverting differentiator circuits. So in this example, I have taken an RL inverting differentiator circuit. We are supposed to find out what happens when I apply a step, what happens to the circuit when I apply a step input of 5 volt magnitude. So the previous examples we took a 10 volt magnitude. Now we will take a 5 volt magnitude and see what happens. The opamp is the same. The saturation voltages are plus minus 10 volts. The time constant here is 1 millisecond. Okay. But here we are only interested in calculating the step response, not a pulse response, just the step response. And the value of the resistance is given to be 1 kilo ohm and the initial inductor current is 0 ohms. You are supposed to find out what is the output voltage and the inverting node voltage Vx of t for all time. Now, even before we start analyzing the circuit, we have done enough passive circuits and active circuit analysis to be able to analyze a circuit like this just using intuitions, right? So we'll use intuitions and do a first quick analysis. What happens at t equal to 0? There is a sudden step change of 5 volts. When a sudden input is applied, the inductor will act like an open circuit, or it will act like a constant current source, which means its incremental impedance is infinity. Its current cannot change. So inductor will act like an open circuit. So which means there will be no path for the current to flow through the resistor. So the voltage drop across the resistor has to be 0. So this node voltage, the inverting node voltage Vx of t will come to 5 volts. So input is at 5, this node will also come to 5. There is no path for the current, so that will also come to 5 volts. That's like a huge negative differential input appearing across the op-amp's inputs. So that will lead to op-amp saturating at the negative rail, which is minus 10 volts. So initially the op-amp suddenly jumps to minus 10 volts when the step arrives. Now in the steady state, when you wait for a very long time, inductor will eventually act like a short circuit. The voltage across the inductor will become 0. So it will act like a short circuit here, and it can carry a finite current. I mean, inductors can carry a finite current even though the voltage across them is a short. So in the steady state, the circuit will reduce to something like this. So the inductor will act like a short circuit, so there will be a DC feedback. So if this node voltage is at 0, Vx will also come to 0 and V0 will also go to 0. So V0 is 0, Vx is 0, and the current flowing through the resistor is given by 5 by R. In this case, R is 1 kilo ohm. So the current will be 5 milliamps. So you will have a 5 milliampere current flowing in this direction into the op-amp. Output voltage is at 0 and the inverting node voltage is also at 0. So this part is clear, right? You can just analyze this just using intuitions. The output voltage, when the step arrives, the output goes to minus 10 and eventually it goes to 0. What happens in between? How does it reach the 0? Does it go through a pulse, or does it have some kind of a discharging, or what? How does the response look like? That's what we are interested in, and we'll analyze that in this lecture again. Okay, so I'm saying this because in the previous lecture I forgot to give you the motivation as to why this analysis is needed. So I'm just stating here, you can analyze the circuit using intuitions itself. What happens in the boundary conditions at t equal to 0 and at t equal to infinity. Okay, in the steady state and at the step event, that's the transient event. Okay, so now we will do a more detailed analysis. So first, as we did previously, we will first find out the value at t equal to 0 minus, that is just before the step has arrived. So input is 0 and inductor, we can treat it like a short circuit. So meaning the output and the inverting voltages will be at 0. Op-amp is a negative feedback, proper DC negative feedback, and output and the inverting voltages will be 0. So that's what I've written here. V0 of 0 minus, Vx of 0 minus, both are at 0. Now comes the moment of truth, that is you are applying a sudden step input. The instant you apply the step input, until now, until t 0 minus, the op-amp was in negative feedback. The instant you apply the step input, the current through the inductor cannot change instantaneously, which means what would happen? It will act like an open circuit. So if it acts like an open circuit, the circuit reduces to something like this. It will act like a constant current source of 0 value. I can treat that as an open circuit. So no current flows to the resistor, so Vx comes to 5 volts. Suddenly it will jump from 0 to 5 volts at t plus, 0 plus. When Vx jumps to 5 plus, since there is no feedback, right, the inductor is now open circuit, so there is no path for output to impact the inverting terminal. So it's like an open circuit, so there is no feedback. Since there is no feedback, the op-amp is in open loop and there is a huge input differential voltage of minus 5 volt appears across it. See, Vx is plus 5, Vd is minus Vx, V plus minus V minus, which will be minus Vx, is minus 5 volts. That's a huge input negative differential voltage. So output will go to minus 10. It will go to one of the negative rails, which will be minus 10 volts in this case. So this is also clear. V naught of 0 plus comes to minus 10 and Vx, this node voltage, goes to 5 volts. Since the op-amp now is in open loop and it is saturated, we can the op-amp is no longer playing any role. So you have a circuit where Vx is at 5 volts. Right now it is at 5 volts and op-amp's output is at 10 volts. Even though op-amp is present, it's in the saturation regime, so its output is at minus 10. So in this region the incremental gain is 0. So there is no negative feedback action, so I can remove the op-amp and replace it as a voltage source of value minus 10 volts. So now the circuit reduces to a simple series RL circuit, and we'll see what happens to this internal nodes. So the input voltage is now at 5 volts. The op-amp's output is at minus 10 volts connected to one of the inductor terminals. This common terminal, this is the inverting terminal, is at 5 volts right now. Now since this is a simple RL circuit, we can easily find out, first order RL circuit, you can easily find out what will be the voltage Vx for all time. We know the initial voltage, which is at 5 volts. That's what I've written here. Initial voltage is at 5 volts. And what about the final voltage? This is an series RL circuit. So in the steady state, the circuit will reach a steady state when inductor acts like a short circuit, meaning the current through the inductor will remain constant. That will be the steady state. So if the inductor has to carry a constant current, the voltage across the inductor has to become 0. So this node voltage will come to minus 10 volts. So Vx starts off at 5 volts and eventually it tries to reach minus 10 volts. So that's what I've shown here. Vx starts at 5 and tries to reach minus 10 volts. But as this node voltage Vx is decreasing, and when it reaches 0 volts, now we will be reaching the high gain region of the op-amp. Then the negative feedback action kicks in, the op-amp action kicks in, and then the op-amp will respond to it in such a way such that this is something we have already analyzed it, but I'll just show it for this case. So now this node voltage is at 5 volts. Bx has just reached 0. The op-amp's output is at minus 10 volts. See, remember, your node voltage Vx was starting from plus 5 and trying to go to minus 10. So until this point, until it reaches 0, Vx is always positive, which means Vd is always negative and greater than and it's always less than 0. So V0 was staying put at minus 10 volts. But when the moment Vx reaches 0 volts, the differential input becomes 0. Now op-amp starts playing its part. At this instant, remember, the voltage across an inductor can change instantaneously. The current cannot change instantaneously. Okay? So it's just that the current cannot change instantaneously. So using that logic itself, you can argue that if the current, see, what is the current through the inductor? It is same as the current through the resistor. If I say the current through the inductor cannot change instantaneously, then this node cannot change. It means the current through the resistor also cannot change instantaneously. What does that mean? Which means this node voltage cannot change. Vx has to stay at 0. But V0 will change. That can have a sudden changes, which is what happens in the circuit. So when your output voltage, when the node voltage Vx goes slightly lower than 0, your output voltage will start rising from minus 10. It will try to reach plus 10, but as it's increasing and reaches 0, the voltage across the inductor will come to 0. When the voltage across the inductor comes to 0, the current can no longer change. At that point, inductor was carrying a current of value 5 by R, right? See, we initially, when we began the lecture, we calculated what will be the steady state current that the inductor will carry. That was equal to 5 by R. And we just saw that the inductor starts carrying the current 5 by R the moment Vx reaches 0. At that point itself, it starts carrying that current 5 by R. So therefore, at that moment, when your Vx goes to 0, your output voltage will rise from minus 10 to 0 and stay there forever. So when it reaches 0, the current in the inductor is 5 by R, it is fixed, it's not going to change anymore. And V minus will also be at 0, and there is no incentive for any of these node voltages or currents to change anymore. So therefore, the circuit has reached a steady state. See, it reaches a steady state abruptly. Now, why does this behavior happen? Because you have a nonlinear, opamp is modeled as a nonlinear element here. So whenever you have such nonlinear elements, okay, the opamp's gain is very high. I have not shown the finite gain here. Whenever you have such nonlinear elements in the circuits, you can expect some abrupt changes in the outputs. Okay, only then you will see such abrupt changes. Normally in LTI systems, you won't see such changes. You will see in nonlinear circuits. Such sudden changes in the outputs can happen in nonlinear circuits with characteristics that look like this. Okay, so output voltage will suddenly reach 0. You can also explain this the same way that we did in the previous lecture. We can assume that the op-amp's gain is finite and assume that since the saturation voltage is assumed to be 10, the point where the op-amp's gain will be very high, it will be in this region of minus 10 by A to plus 10 by A. In this region, the gain will be very high. So as your node voltage Vx is decreasing from 5 volts, when it reaches a voltage of 5 by A, when it reaches a voltage of 10 by A, so that's V sat by A, what will happen? You will be at this point. So initially your Vx, your Vd, the differential input is minus Vx. Initially your minus Vx was at minus 5, your Vx was at 5, so Vd was at minus 5. As your node Vx voltage decreases, the differential input to the op-amp also decreases. And then it enters the high gain. The op-amp will now enter the high gain region. The moment the op-amp enters the high gain region, I can now treat the op-amp as an amplifier with a gain A. Now I am trying to find what this node voltage will be. I have a resistor connected to one end, and the other end, this node is connected to an inductor with an op-amp around it. So this circuit, we can use Miller's theorem and show that it can be approximated to an inductor of value L by 1 plus A. Okay, at this instant, for the moment we enter the high gain region. So now it will start charging. This node voltage is at, right now, this node voltage is at 10 upon A. Before 10 upon A, this inductor value was L. Okay, after 10 upon A, once your node voltage Vx starts decreasing lower than 10 upon A, suddenly the inductance will appear like a much lower inductor value. So now the time constant will become RL by 1 plus A, and we showed that suddenly you will have a step change in the time constant here. Here it was L by R. Here it will become, this should be L by R into 1 plus A. Okay, that's the time constant. So here it is L by R, and here it will suddenly decay much faster to 0 volts. So your output voltage can then be written as, since your output voltage V naught of t, when you enter the high gain region, it will simply be equal to minus of Vx of t times A. So before that, before this reaches 10 by A, your output voltage was staying at minus 10. Once it reaches in this region, it will simply be minus of Vx times A. So take 10 by A, multiply with minus A, you get minus 10, and then the waveform will look something like this. The time constant here is much faster, much lower of value, much faster in time. It will discharge very quickly from minus 10 to 0 volts. So that's what happens here. And if you assume A equal to infinity, we said that you can model this time constant will go to 0. So that which means it will immediately drop from minus 10 to 0 volts. So this is what happens in this circuit. And if you want to exactly find the value, the width of this pulse or the time at which the output signal goes from minus 10 to 0, you can use our standard equations, first order equations. So this is the point, the on time of the pulse is given by the time at which the node voltage Vx goes to 0. If you find that, assuming the step arrives at t equal to 0, the on time will be the time at which the node voltage Vx goes to 0. So the initial voltage of the node voltage is 5, final voltage is minus 10, Vx of 0 is 5 and Vx of infinity is minus 10, and you can just use that expression, initial value minus final value times 1 minus e power t upon tau plus the initial value should be equal to 0. Find it out. I have done the value. The on time of the pulse comes out to be tau ln of 3 by 2, which is 0.405 tau. Okay. If you recall from the previous example, the on time happened to be 0.693 tau. That's because the initial value started off was 10. It was much higher. The step value was much higher. So it took longer time to reach 0. But now you are only 5 volts. So the time it takes to reach 0 is smaller. So that's why it is 0.405 times tau. Assuming tau is 1 millisecond, it will be 0.405 milliseconds. So now that we have all this information, we will be able to draw the steady state pulse. So if you apply a step input of 5 volt magnitude, what you should expect at the output of this op-amp is a pulse output that goes high when the step arrives. It goes to minus 10 when the step arrives, and it stays on for a duration of roughly 0.4 milliseconds. Okay, and then it comes back to 0. See, once your output reaches a steady state, once your input reaches a steady state, output will eventually come to 0, right? It should be derivative of the input signal, so it will come to 0. So only when there is a rising edge event, your output produces some, the differentiator produces some output. Okay, and this on time, I think is 0.405, right? 0.405 milliseconds. So this is how it's going to look like. In case you have any doubts, you can just you can write to me, you can post the comments, I'll get back. Thank you.